Well, when we want to turn this into quantum mechanics, we have to apply our 4 postulates. And so our first postulate would just define our quantum states using these 2 independent states 0 and 1, and we would just have superpositions, and I'm going to write this very generally with some coefficients alpha and beta. And in this basis we can also think of this as a 2-component vector. We also need a scalar product, so let's define another state with coefficients gamma and delta corresponding to this vector here. And then the scalar product would be given by this expression. And when you insert there the examples of vectors as above, you get the same results as before. And when we later want to work out probabilities, it is convenient to normalize our states. So we have this condition for normalization. And we can again define what it means that 2 vectors are orthogonal to each other, namely that this scalar product here just vanishes. So this would be just this scalar product here. Next we turn to the observables. Well, these need to be linear Hermitian operators, and these then can again be written in terms of 4 elementary operators. The identity operator and 3 operators related to the Pauli matrices. And now let me write these down in Dirac notation. So the identity operator would just be this operator here. And X would be this operator. Y is this operator. And Z is this one here. Let us, for instance, look at what X is doing to a general state. Well, here we will obtain scalar products between the state 0 and 1, which vanishes, and the state 0 and 0, which will give us 1, because we assume that these basis states are normalized, and therefore we obtain alpha times 1, and then we have a scalar product between 1 and 1, which is just 1, but multiplied in front of the state 0, so this gives us beta 0, and then we have a scalar product between this term, and this just vanishes again because these states are orthogonal. So this corresponds to the vector. Well, now we have the alpha in front of the 1, so this is down here, and the beta is in front of the 0, so we have this one here. Now this is the same as applying the Pauli matrix sigma x to the state alpha beta. So it's the same as applying this matrix here, because this is just a permutation matrix that gives us the same result. And this works in the same way with the operators y and z. Let us look at the eigenvectors of these. Well, again, I just do this for the example of x, where the eigenvectors, one of them can just be written like this, because we have just established that x converts the 0 here into a 1 and the 1 into a 0. So this becomes 1 plus 0, but this is of course the same as 0 plus 1. And that's again the same as multiplying our original state by 1. So this is an eigenstate with an eigenvalue 1. There should of course also be a second eigenstate, and this should indeed be orthogonal to our first one, which we obtain by putting a minus sign here. This now gives us this expression, which is the same as our original state when we put a minus sign in front of all of this. So this is now an eigenstate with eigenvalue minus 1. So these are two eigenstates of x. They're not yet the normalized version, but these we obtain by just dividing by 1 over square root of 2. So we have these two states, And I'm just going to denote them for future reference as plus or minus. One can also work out the eigenstates of y and z. For y, I introduce two states plus or minus I, and this is just a notation. They are defined in the following way. In terms of normal vectors, they just look like this. And the corresponding eigenvalues, again, plus or minus 1. And for z, this is even simpler. This has just one eigenstate, which is this state here, corresponding to this basis vector. And this has an eigenvalue 1. And the other eigenstate is just the other basis vector, so corresponding to this vector here. And this has an eigenvalue minus 1. So all of these three operators, x, y, and z, have the eigenvalues plus and minus 1. And these indeed just correspond to special cases of the general expression for eigenvalues of 2 by 2 matrices that are given above. And we can indeed employ this now when we look at the dynamics of quantum systems, because the Hamiltonian is just a very special Hermitian operator. So we can again write it in this form here. Now these coefficients a, b, c, and d could depend on time, but we are not yet at the place where we should discuss these more complicated dynamics. So let us just look at the stationary Schrödinger equation. But this is just an eigenvalue equation. So there will be two quantized energies, and their values are just given by this expression here. So not much to say in terms of dynamics, and therefore let's turn to measurements. So in measurements, we do measurements on observables, which are represented by these Hermitian operators. And for example, we are going to consider the cases of the observable x and z. The possible outcomes of the measurements are restricted to the eigenvalues, so to +1 or -1. And these outcomes occur with probabilities, where for instance the probability to observe the outcome 1 is obtained by taking the absolute value squared of the scalar product between the state of the quantum system and the corresponding eigenstate. So the state plus here. So this would be the absolute value squared of this complex number. There we can then introduce our general expressions, including expressing this state here in terms of the coefficients alpha and beta. And then we obtain this expression here. We can also do this for the other outcome. So the outcome minus, we just use the other eigenstate, and then we obtain this result here. And then one can, for instance, check that these probabilities add up to 1, provided that our quantum state is indeed normalized. In the case of the observable z, this is even more simpler, because our eigenstates are just the basis states. So here we just have the scalar product of the quantum state with a basis state, which just projects out the coefficient alpha. So the probability is alpha absolute value squared. And for the other possible outcome, -1, we then obtain just beta squared. And the sum of these is indeed again 1, just by the normalization of our original quantum state. And from there we can then also work out expectation values, either just using these probabilities or our general expressions. So in particular we can work out expectation values of x using the probabilities, or just using this expression here. And in both cases this just comes out as 2 times the real part of alpha complex conjugate times beta. And again you can get similar expressions for the other observables, such as for y. This turns out to be 2 times the imaginary part of this combination of coefficients. And for z, we have this expression here, which turns out to be alpha squared minus beta squared. We can also work out uncertainties, but this is indeed very simple because all of these operators here square to the identity operator. This is most easily checked by just using the 2x2 Pauli matrices. So just squaring the Pauli matrices, you always get the identity matrix. So you see that all these operators have some very simple and useful features. Well, there is another one, namely if you take the product of two of them, the result is proportional to the third one. And furthermore, you always obtain the opposite result when you multiply these operators in opposite order. And this, for instance, means that the commutator between x and y is just 2 times I times z. From there we can then, for instance, write down a general uncertainty principle for the product of the uncertainties of x and y. So this is never less than 1/2 of the absolute value of the expectation value of this commutator. In here this 2 cancels and the absolute value of I is just 1. So this is given by the absolute value of the expectation value of z. Well, here there are indeed some states for which the expectation value of z vanishes. So these absolute values just need to be the same. And examples of these are indeed the eigenstates of x and y. And in these eigenstates, indeed, the corresponding uncertainty vanishes. So this is indeed now possible. So you can have 0 at both sides. So this is certainly qualitatively different from the uncertainty principle for a point particle in 1 dimensions, where you just have a fixed number on the right-hand side. And for instance, when you try to make this one very small, then the other uncertainty becomes very large. But this is not possible for this two-state system, just because these expectation values are finite and indeed always lie in the range between -1 and +1. And this just again highlights the simplicity of these two-level systems, because we always just deal with two complex numbers, alpha and beta. These two-level systems have many applications, and we will later encounter them in the context of spin, but they are also often used to approximate quantum systems. So for instance, when we have an electron that might be confined to 2 different regions, and when we work at very small energies so that there are really only 2 states available to this electron, then we can just describe this in terms of these 2 states that we can label as 0 and 1. Or this could be a diatomic molecule, so we have 2 atoms, and then we have 1 electron in here that we are particularly interested in because it is involved in the binding between the 2 atoms. And so when we reduce it to a 2-level system, then we obtain 2 states with different energies, and one of them we would call the bonding state. That's the one with a lower energy, and the other one we call the antibonding states. Motivated by this example, let me briefly extend this into another discrete quantum system. We call this a tight binding system. And the idea is that we have a chain of atoms, and this chain might indeed be infinitely long. But what we are going to use is that this is a periodic system. What we're interested in is again just a single electron, and the physical picture is that this electron can hop from one atom to another. To describe this electron, we introduce a state psi, which just tells us at which place the electron is sitting. So all of these basis states are just indicating the position of the electron, which we enumerate by an integer, which can range from -infinity to +infinity. And the probability to find the electron at the position n is given by the absolute value squared of the corresponding amplitude. There we are again assuming that our state is normalized. So this sum here, ranging over all possible positions of the electron, possibly from -infinity to +infinity, should be 1. Now we could develop the complete quantum mechanics of the system, including observables and measurements, but what we are going to look at here are the energies of the system in one particular situation. And there we assume that the electron can only hop from one atom to its neighbors, either to the right and to the left. And we attribute a certain energy to this. We call this T, and by convention one puts a minus sign in front of this. And then one writes down a Schrödinger equation in a very concrete form, which has this form here. This corresponds to a certain Hamiltonian that can be written as a matrix. And in this matrix we have zeros on the diagonal and minus t on the next off diagonal, and I put the minus sign in front. So I just place t here. And then all the remaining entries are again 0. And this can be interpreted as a potentially infinitely large matrix. And even though this is infinitely large, this has a very simple solution. Because we can stipulate that the solutions psi n are of the form of a plane wave. And here we have the wave number, and this is then multiplied by the position, but this is now discrete. We are going to say that the distance between the atoms is some certain length, little a, and then the position of the electron would be n times a. When we introduce this function into the Schrödinger equation, we now obtain a factor e to the I k n a in every term. So we factor this out. And then we get some additional contributions from this minus 1 and this plus 1. And this just becomes e to the minus ika and e to the plus ika. So we can cancel these common factors and read off the energy immediately. So this can be written as minus 2 times t times cosine ka. Let us place this into a diagram and then we are done. So we have E as a function of k, this wave number, which is also known as the crystal momentum, because what we essentially describe here is an electron moving in a crystal. And then we have this cosine with the minus sign in front. So this looks roughly like this. I've just plotted over one period, centered at the origin. So these are the values pi over a and minus pi over a. And here we have t and minus t. And this, as I said, can be interpreted as describing the motion of an electron in a crystal. And in this context, this is known as the band structure. So this is the simplest version of such a band structure, but this really forms the basis of a very detailed theory of the electronic structure of materials. What you then would do is to add a three-dimensional crystalline structure. And model your atoms more realistically. For instance, accounting for their internal states. And also perhaps considering more than just one electron. And then you obtain increasingly more realistic descriptions of materials such as semiconductors and metals. And one can extend this even further to other features, for instance to see whether these materials are magnetic or display superconductivity. But that makes these questions more and more complicated, while my message with these videos is really the opposite. Namely that quantum mechanics for systems with discrete states is really quite simple, in particular if there are only two states. And this we are going to see soon again when we discuss the quantum mechanics of spin.